Hi, everyone, and welcome back to our next episode of Topics in Neurorehabilitation presented by Robotics. I'm Derek Onati, and today we'll be talking with Dr. Gregory S. Sawicki, Associate Professor at Georgia Tech with appointments in the Schools of Mechanical Engineering and Biological Sciences in the Institute for Robotics and Intelligent Machines. Dr. Sawicki also spends part of his effort as a senior research scientist at the Institute for Human and Machine Cognition in Pensacola, Florida. Dr. Sawicki directs the Human Physiology of Wearable Robotics Laboratory, where the goal is to combine tools from engineering, physiology, and neuroscience to discover neuromechanical principles underpinning optimal location performance and apply them to develop lower limb robotic devices capable of improving both healthy and impaired human locomotion for elite athletes, aging baby boomers, and post-stroke community ambulators. Dr. Sawicki will be speaking with us today regarding exoskeletons for improving mobility post-stroke. Hi, Dr. Sawicki. It's a pleasure to speak with you today.
Hi, Derek. Thanks so much for the invite. I've been following these online for quite some time now, so it's good to actually be here. And I'm excited to tell you what we're up to today.
It's fantastic. I'm excited to hear about the research you've been conducting in your lab to help improve the gait of individuals recovering post-stroke through the use of robotics. Technology has become such a crucial tool in the treatment of patients and helping clinicians provide better outcomes through targeted specific training. And I can't wait to hear your thoughts on the field of robotics and where the research is taking us. To our viewers, we'd love to hear your thoughts in the comments below. And don't forget to like this video and subscribe to our channel and Clinicians Corner blog for more exciting content. And with that, Dr. Sawicki, I'll let you take it from
together. I don't know, maybe a 20-minute presentation on, I guess, the road we've taken in stroke rehab as a topic. And so I'll talk a little bit about some of the basic science work that we do to underpin our strategies for robotic intervention. And then I'll tell you a little bit about our failures and hopefully upcoming successes in using robots to improve mostly the metabolic cost of walking in stroke, but more lately we're focusing on self-selected walking speed as well. Okay, so there's been two kind of main questions that my lab is focused on, and these have been huge collaborative efforts. So I'm going to shout out some people at the beginning, and then you'll see these faces reappear on a project by project basis as I go. I was at UNC Chapel Hill and NC State in biomedical engineering for, I guess, 8 years before I moved to Georgia Tech in 2017. So this research really goes back quite far, over a decade. And really, I have to credit Mike Lewick. I know Mike's been a guest on this show as well, on this series. Mike really is the one who got me interested and I guess amped up about applying some of the expertise I have to stroke. So you see Mike there, and then Kate Saul is a colleague in mechanical engineering at NC State who kind of joined the team later. And really these three people up top, Dominic Ferris was a postdoc in the lab, and then Austin Hampton and Caitlin Mahan, who were co-advised by me and Mike Lewick, led the early work, which is just kind of reframing the basic science of what happens post-stroke at a joint level. We always like to do that as a precursor to intervening with robots. We want to know which joint we should intervene at. So I'll tell you a little bit about that work first. And then that led into many years of using both powered, I'll tell you only about powered devices today, but powered and passive ankle devices to try and improve propulsion and reduce metabolic costs post-stroke. And that work was really started off being led by Kota Takahashi, who's now a associate professor at University of Utah. Emily McCain was sort of the lead student, co-advised by myself and Mike Lewick, Kate Saul, that led the later work. And then this other team of collaborators, Tracy Geist is now at Fitbit. She was a postdoc in the lab. Taylor Dick, who's at University of Queensland now, and Rich Knuckles, who just started at University of Waterloo in Canada. So I'll focus on these two big topics, hopefully in tidbits of interest. Oh, yeah, I also need to mention that since moving to Georgia Tech, team's grown even more, right? So recent collaborations mainly with Aaron Young's group to try to move into using hip exoskeletons, along with Kinsey Heron and Trisha Kezar over at Emory has helped us with some biofeedback aspects of the work. And then these are the two students who have so far really led our efforts, Emily Upton and Amy Pan. Okay, so, you know, many in the audience probably know a lot of the biomechanics post-stroke, but I just want to kind of review that. we revisited this question, I guess in 2012 or something like that. Myself, Mike Lewick, Dominic Ferris, and Austin Hampton. We applied a simple inverse dynamics analysis to look at what happens at the joint level post-stroke. So you could see down here, and these data were not novel at the time. We just wanted to kind of recouch things in a mechanical work framework. But here, what you're looking at is ankle joint power output on the y-axis, and then this is plotted over a stride. And the different curves represent in gray a control limb, and then in black the paretic side of a stroke survivor, and in dashed black the non-paretic side of a stroke survivor. So what I want you to notice right off is the deficit in push-off power, which is, you can compare right here in black to gray on the paretic side. And really not too much difference, maybe a small compensation, a little bit more of a push on the non-paretic side of the ankle. What's interesting though is the compensation that happens as a result of this, that we see this sort of classical ankle hip trade-off where, because of asymmetry and push off at the ankle, people need to rely much more heavily, especially on their non-paretic hip early in the stride in order to generate propulsion. Okay, so that, if we look at this a little bit more closely, we like this pie chart analysis in my lab where we could integrate under the mechanical power curves to get an idea of how much work each of the joints do. And we can understand what each joint contributes with respect to a total work output of the limb. So what you're looking at here is color coded in white, which is hip, black, which is ankle, and gray, which is knee. If you look at let's first look at the control side. So the pie chart on the right at the top, you could see that workload is split evenly across the right and left legs, and that's because there's symmetry in a young person's gait, a young able-bodied person's gait. And what you can see is that the way that the workload's broken down is most of it comes out of the ankle, 43%, the hips in a close second. And this was speed matched at a relatively low speed, 0.75 meters per second, to make an apples to apples comparison between a stroke survivor at around the community ambulation speed and their healthy age-matched control. Now on the left, for the hemiparetic gait, you could see a bunch of key differences. One, there's this asymmetry showing up, so more mechanical work comes out of the non-paretic limb versus the paretic limb. The total amount of work goes up, so you have to do more total work because of your asymmetry. And then the way in which that work is done also changes. The more heavy reliance on the hip than there is on the ankle. Okay. And what this leads to, we think, this is what underpins the increase in metabolic cost that a stroke survivor has to manage. And that increase can be up to 50%, even at that slow walking speed. So that's a big deal. That's like, I would say that's like carrying, 2 or 3 heavy backpacks of load, like with your laptop and your school books. So it's a burden. Many years later, we revisited this question because we're interested in trying to understand more clearly the sources of those increases in mechanical energy and metabolic cost. And this is a study that I know Derek has seen and asked me to talk a little bit about, that was led by Emily McCain in conjunction with Kate Saul and Mike Lewick. And here we didn't study stroke survivors. Instead, we used what we call a surrogate stroke model. So we constrained the lower limb joints sort of in a very systematic way to try to simulate the gait biomechanics that you might see, for example, from stiff knee by locking the knee, or reduced propulsion by locking the ankle. And then the combination of those two things, which is what most stroke survivors present with. Now, what's difficult is to tease apart the contributions of, say, a stiff knee versus a lack of ankle propulsion in a stroke survivor without just, getting lucky, I guess, that there's natural variability in the participant cohort. So here we use able-bodied surrogates to simulate by constraining joints some of the key issues we see post-stroke, and then we can kind of follow the cheese through the mechanistic pathway to try to understand which of these issues might be impacting energy costs more. So this is just a brief bit of data here. You should go to the publication if you want to deep dive. But the intervention worked. We could create kinematic patterns at the knee and ankle that look very much like what happens post-stroke, just by restricting the joint motion. And what we were interested in then is like, what are the limb level outcomes of each of these restrictions? And then what are the whole body metabolic consequences of those? And these were all, by the way, these are all just unilateral restrictions. Again, going along the playbook of post-stroke where we have restrictions really only on one side. We've since done a follow-up study where we checked symmetry. So we would lock both sides versus a single limb. And that's I won't have time to talk about that today, but there were some interesting things there as well. So what did we find? Well, key thing is that this shouldn't be surprising, but when we locked the ankle, people had lower propulsion on the locked side. When we locked the knee, there was no significant reduction in propulsion, which may or may not be expected. But then when we locked both the ankle and the knee, that these statistical decreases in propulsion returned. So this really, I guess, like makes the point that the ankle is a locus of importance, that if you restrict the ankle, no matter what else you do to the limb, restrict even the knee, you end up with these reduced propulsive forces on the ground. So that's not good. We don't want a restricted ankle. And if you do a further analysis, you can see that ankle restriction is associated with increased mechanical work at the hip, the sagittal plane, kind of like that hip ankle trade-off that I showed before. What's interesting here is it's worse when you only restrict the ankle versus when you restrict both the ankle and the knee. That was kind of unexpected. So again, just re-highlighting and I don't know, more strongly establishing the idea that lack of ankle propulsion is a big deal for gait biomechanics. If you look at what happens when you to circumduction, which is another sort of key symptom of in post-stroke gait, where people, because they can't flex their knee at the right time into the right amount, that they have to use what we call a hip hiking strategy. So they have to find ways to either tilt or tip their body so that they can clear their swing leg during swing when they can't flex their knee as much as they'd like. So here, this was just kind of verifying that indeed, when we lock the knee, that's where the knee lock seems to be associated with the hip circumduction rather than say the locked ankle, where we found no. If you lock a person's ankle, they have no problem with swing, so they can still kind of do business as usual during swing phase. The other thing we found is that in the locked knee and locked ankle and knee, we found direct evidence that people were using a pelvic list or a pelvic tilt to avoid scraping their swing leg on the ground. So again, it's a nice way to kind of dissect out the common symptoms that we see in gait biomechanics post-stroke, but in a more systematic way using healthy controls. And it verifies a lot of what the literature, I guess, was assuming mechanistically, but in a very causal way here, where we know what each of the, ability challenges in isolation due to the overall limb level biomechanics. Metabolic costs went up. Again, it shouldn't be that surprising, especially in conditions where the ankle was locked. We found significant increases in metabolic cost. Just by locking the knee, people were able to move with a non-statistically different metabolic cost. So that's kind of interesting. It seems, again, the locus of the increase in energy costs has to do with lack of propulsion of the ankle. And what this really does is this is sort of hindsight 2020 of this study, because I think before this, we'd already been focusing on the ankle, but maybe not based on causal experiments like this one. So this was just, a pat on our own backs and a pat on the backs of people in the field who, I guess, had been assuming, without doing really direct causal studies, that propulsion was the issue that is most responsible for increased metabolic cost. Okay, so now we'll seg into the exoskeleton section of the talk. I've been working on exoskeletons for a long time now, all the way back to grad school, mostly ankles, a little bit more hips lately. But this is a review paper that myself and a few colleagues from Georgia Tech published, I don't know, I guess a couple of years ago now, just showing that the field has gotten better and better at figuring out how to time mechanical assistance and also with what magnitude mechanical assistance should be delivered in order to get what are now pretty large reductions in metabolic costs. And these are all data from healthy young adults mostly. There's a similar trend, I would say, in the stroke literature, although we're not getting to reductions of 20 and sometimes now 50%, which isn't even on this graph. The latest data that I've seen is 50% reductions for bilateral assistance at all three joints. That's coming out of Steve Collins's lab at Stanford, who we've collaborated with a bunch. Stroke, I think, is a little bit, I would say it's probably 5 or 6 years behind. And the reason is because understanding and figuring out how to time assistance, but also where the assistance should be applied, say ankle versus hip, we're not all the way there yet. So I expect these numbers will continue to drop. And I think we can approach 30, maybe even 50% reductions, even in a stroke survivor. And that's kind of the goal, I think, for us long-term is to really make a big dent, to even get the stroke survivor to be able to walk with less cost than their age-matched, able-bodied counterpart would be really cool. So how did we tackle this at first? Well, like I mentioned, this was work led by Kota Takahashi in collaboration with Mike Lewick. And what we did here is we use proportional myoelectric control, which is a control technique where you borrow the timing and magnitude from the person's own physiology. So you record from a surface electrode. In this case, we recorded from the soleus muscle of a cohort of stroke survivors. And we use that signal to directly drive the action of the robot. So the idea here is that, like, if you can put the robot under direct control of the user's nervous system, adaptation and learning, or relearning in this case, may be able to proceed more quickly. So that's what we tried. We added a little twist here because EMG activity is a little bit different post-stroke than it is for a young able-bodied person. And in particular, the timing of the plantar flexors tends to be earlier onset than what is normally observed in controls. And so to account for that, we didn't want the exoskeleton to turn on too soon and push people backwards. But we did still want people to be in control of the device using their own electromyography. So we added this thing called what we call a ground reaction force gait. And in this case, they're on a treadmill. So we knew when propulsion began. And we only allowed the exoskeleton's control signal through when people were trying to push themselves forward. Now, off the treadmill, you could do that with, say, like an instrumented foot sole or something. So this would be possible on a device, on an autonomous device that ships outside of the lab as well. Here's just a little tidbit of sort of how this thing works and using some data as an example. So up here, what I'm showing in green is the EMG signal from an exemplary participant in our experiment. And in black are the anterior posterior ground reaction forces. So when the AP ground reaction forces are negative, the world is pushing backwards on the person. That's like early in the stride. And then when that flips to positive, that's the person propelling themselves forward. So you can see here that the activity, the locus of EMG is focused early in the stride for this person, which is, again, typical post-stroke. Down here, I'll eventually show you what the artificial muscle, this is a pneumatic muscle control signal was, and what the force coming out of that is. And then I'll show you how the ankle mechanical power changes when the device is on. So this is just a plot showing what the ankle mechanical power output is with the exoskeleton off. What I want you to focus on is these peak positive values when we turn the exoskeleton on. So what we're trying to do here is make these peak propulsive power outputs larger by giving the person mechanical assistance that they're in control of with their own EMG. Okay, so when we powered it on, this really cool thing happened. And again, this was an exemplary subject. We didn't see this in everybody, but this would be awesome if we did. You could see that some EMG activity is now appearing during the propulsive phase. And that's interesting. So this person's volitionally understanding that they have help, and I don't know what you'd call it, maybe priming or something like that. There's some kind of neural activity priming where they learn, and this is not in the first few steps. This is after a little bit of use. They learn that they can get the help from the exoskeleton by turning on their own soleus EMG in the right place in time. And what that leads to is like artificial muscle forces that also are aligned with the push-off period. And again, this was an exemplary subject. We didn't see this awesomeness in every participant, but for this person, they were able to increase, they were able to use the red contribution from the exo to increase their total ankle mechanical power output by quite a bit. It looks like almost double here in some steps. So that's awesome. What that led to on average in this cohort of, I think, only 6 stroke survivors, this was really a feasibility study, was a slow decline in metabolic energy costs. Again, we're trying to beat this black bar here, which is the cost of them walking without the exoskeleton on. We put the exoskeleton on, and you got to carry that added mass around. So there's a burden just to wear the device. That's what this red bar represents. And then what we're trying to do over time is get these blue bars back under the level of the dashed horizontal line so that there's actually a net benefit of the device. We weren't able to see that in this cohort. Each of these blue bars represents another 5 minutes of practice. So they've only practiced for a total of 15 minutes, which probably isn't enough. And the trend's going in the right direction. And so, we're still to this day working on follow-up studies in larger cohorts where we have people walk for much longer using assistance like this, so we could see whether or not we can get net benefits over a longer time course. So that device was cool and everything, but we decided, well, maybe part of the reason it's not working well is because they're walking on a treadmill at fixed speed. And if we let people explore the speed range that they're capable of, maybe we would see benefits sort of at the high end of their walking speed ability. So we embarked on a second study. Again, this one was, the data collection was led by Tracy Geist. This was an NIH-funded R21. And Emily McCain kind of took the wheel after Tracy left for Fitbit. But here it's the same device as before, a little fancier in terms of the mechanical design. But the same EMG-driven ground reaction force gated control, except this time we made sure that the device could handle increased speed. So we fed information from a speedometer on the treadmill into the exoskeleton control. Again, if you were off the treadmill, this could come from GPS or some other speed measurement. And we used that to increase the assistance in proportion to the locomotion speed. So at higher speeds, they're getting more out of the exo. And then we did this in a protocol where we bumped up the walking speed every, I want to say it was 30 seconds. It might have been a minute. Maybe it was every minute we increased the speed in a sort of stepwise progression. And again, so we could start with a person with below a person's overground self-selected walking speed at about 0.6 of that. And then on the treadmill, take them all the way up through a speed where they either said, no, I don't want to go any faster, or their heart rate came within the threshold of maximal that we were comfortable with. Okay, so they could either tap out themselves or they just went until their heart rate got too high. And what you could see here is these graphs, the gray is going to be the unassisted condition. So the exoskeleton's off, and the blue is going to be with the assistance on. And you could see here that the net limb power, so the amount of mechanical power, that total pie chart coming out of the paretic limb, which is in bold. Sorry, this is the non-paretic limb. So you could see that the exoskeleton in the assisted condition isn't really doing much to the non-paretic limb. But if you look at the paretic side, we can actually shift people from net negative work to net positive work by giving them the exoskeleton assistance. And at very, very fast speeds, we have a good amount of net positive work coming out of the leg, which is great. That's good. If you look at where that comes from, well, this should be obvious. It's coming from assistance at the ankle. So this is the net power or the net mechanical work. So the ankle in people without mechanical assistance on the paretic side is acting like a brake, actually. So stroke survivors are absorbing net energy in their ankle in this experiment. But when we put the exoskeleton on, we're able to switch it to a motor. So they're using the exoskeleton motor to overcome their nominal braking action. Here was this was the, I don't know, less exciting part. We weren't able to convert these good changes in mechanics to reduce metabolic effort. And again, this is sort of what we've been struggling with in our lab for a long time now, is we can do really good things mechanically, but we're not able to reliably convert those mechanical improvements to changes in metabolic costs. So we really started delving more deeply into that, like why does that happen in this experiment? And Emily did an amazing job thinking about all the sources and kind of, I don't know, drawing red lines through candidates as we went, rejecting hypotheses to come upon the idea, which I'll get to in a second here, that I think we're using now to make progress again. So here you can see that again in gray, unassisted percent paretic propulsion. This is a measure of how much propulsion is coming from the paretic versus non-paretic leg. If this were 50%, that would mean you get the same amount of propulsion from both legs. Post-stroke on the paretic side, you're only getting about 20% or 30% at the fastest speeds, which means your non-paretic limbs got to make up that propulsion. So it's like a 70-30 rather than a 50-50 split post-stroke. When we turn the device on, even though all those cool things happen at the limb level, we actually made net propulsion on the paretic limb worse. This was like really disappointing, but it kind of matches with the idea that the metabolic cost didn't really go down. And this is kind of the key thing, is that it boiled down to trailing limb angle. The easiest way to summarize is that our exoskeleton was pushing people up rather than forward. And we think that's because the angle, the posture that they had at the time of push off was too upright. The exoskeleton was encouraging them to, take sort of shorter, more upright steps rather than kind of expand their stride length and push forward. The reasons for that are unclear, but it's a fact that at least this ankle exoskeleton with this controller pushes people up rather than forward. So we're taking mechanical work, putting it into a limb either at the wrong times or in the wrong configuration. Okay, so last couple slides. What are we doing now to try to make that better? Well, one thing is, why do we have to focus so much on the ankle? That the idea there comes from good science that propulsion, which usually comes from the ankle, is reduced post-stroke. So let's try to put a Band-Aid on that, right? Let's try to deal with the source. But another strategy would be to try to assist the compensation. So I told you that normally there's this distal to proximal shift. So people rely more on their hip joint post-stroke, and they do that bilaterally. So that's what we've kind of been working on, my group, along with Aaron Young's EPIC lab at Georgia Tech, and supported by Kinsey Heron, who's a certified prosthetist, orthotist, and a research scientist in our group, and then Amy Pan, who was a postdoc at the time. We started thinking, well, let's just use bilateral hips. And we're not the first to think of this. I think Tommaso Lenzi, University of Utah, has shown some really strong results using bilateral hips recently. So we're trying to get on that train and see if we can also do some things a little bit differently than Tommaso, and maybe with some more bells and whistles to try to do even better than what Tommaso has shown is possible. A key for us is human in the loop optimization. So we're not going to just give people a generic 50, 50 Newton meters would be high, but something like 10 Newton meters on each side. We need to think about the individual's asymmetry and what each individual needs. And one way to do that is use an approach called human in the loop optimization, where we online try to tune the exoskeleton for each individual in order to do something good for them. In this case, it might be improved self-selected walking speed. And so we do that on the treadmill. We fix the treadmill belt speed, tune up the exoskeleton left and right to see whether or not we can improve their walking speed. And then the idea is, like, once we've done it on the treadmill, we want to transfer it over ground. So we'll get some tuning period on the treadmill. This person's wearing bilateral hips, and again, we're tuning up the amount of assistance they get left and right, paretic, non-paretic, based on their feedback. A, how does it feel? Do they like it? And then B, sort of how well they're doing at maintaining higher and higher walking speeds on the treadmill. And then we're checking to see whether or not that same controller works for them over ground. Does it change their self-selected walking speed? Okay, so that's one excited direction forward. The other, which I might even be more excited about, but we don't have results on yet, but this is sort of where we want to go, is to include, and this is what Trisha Kezar kind of comes into the team heavily now, because she's an expert on biofeedback. So the idea here is, if trailing limb angle is sort of a bottleneck, then we should tell people what their trailing limb angle is and ask them to adjust that while they're using the robot so that they can get the most out of it. So we're doing this both for ankle assistance. We use the Defy ankle exoskeletons in combination with a vibratory biofeedback system that tells people when they're hitting a target trailing limb angle that we want them to go to. They go through this complicated protocol, which involves exo only, biofeedback only, and then the combination. And then when we do the same thing, but this time with the hip exoskeleton too. So we're able to answer here, which one of these exoskeleton interventions is better without biofeedback, and then does biofeedback help one or both in terms of the performance of the device? Okay, so that took a little longer than I'd hoped. Sorry about that. Hopefully it was interesting enough for people. And then just to acknowledge funding sources, mostly this work's been funded by NIH through the years, National Institutes of Nursing Research, NSF, National Robotics Initiative, and thanks for listening.
Thank you, Dr. Sawicki. That was a great presentation on a lot of crucial knowledge for all clinicians out there. I really did an excellent job kind of explaining the importance of the contributions of the ankle to paretic propulsion and what happens with restricting it, as well as how important trailing limb angle plays in the contribution to overall transfer of forces to an individual when they're moving forward through space. And I think that's incredibly important research that I know isn't necessarily novel. You know, it's been out there for a little while, but still hasn't, as you said, made its way into the commonplace practice for clinicians out there. I know our viewers will want to learn more, so I do have a few follow-up questions for you.
Great.
You know, ankle foot orthotics, AFOs, have really been an integral part of therapy for a lot of years in physical therapy clinics. You know, it's used daily and allows for safe mobility because it provides obviously distal stability that the user's able to clear their limb. As you said, when they, you know, when you're locking out the ankle, they're more easily able to clear their foot. But the resulting restrictions in propulsive forces and the metabolic cost is really detrimental to the overall ability of the individual to ambulate. You know, what recommendations would you make to clinicians who want to integrate this type of technology into their practice when the standard of care for so long has really been to just immobilize the joint for safety? What should they really start doing to improve the net propulsion, propulsive forces for their patients?
Yeah, that's a great question. I mean, and I think we shouldn't disqualify the importance of, you know, of standard AFOs. I mean, I think they're still incredibly useful. I would say I'm going to answer this in a couple different ways. One is I think for clinicians, you know, be open to the next in AFOs, which I think are coming down the pike. So there, you know, there are a lot of P&O companies and industry now working on versions that have the ability to have range of motion that's not as restricted. And this is going to come from clutching mechanisms and other approaches. So be open to integrating, I guess, the next generation of AFOs into practice is one answer I would give. The other, is I think biofeedback is going to be huge. So what do I mean by that? I mean, even with an AFO that may restrict motion of the joint, there probably are ways to modify the rest of the limb's behavior. Trailing limb angle is something that came up in my talk, and I'll mention it again. So just, by postural changes coming from up the chain at the knee and hip, it is possible to get a lot more out of, I think, the standard therapies like AFOs by training and learning and coaching in partnership with your therapist or with a therapist to teach people how to get the most out of what might be, otherwise restrictive. So those are two things I think. Be open to new technology that might seem scary at first because, the stability and safety you get from immobilization is important, especially maybe early in rehab. Be open to moving to devices that are a little bit more dynamic later in rehab, and then really getting on the idea that we can do, I think, much better even with the standard assistive technology by improving our ability to coach through, say, biofeedback, which might target biomechanical variables that we know are related to propulsion, like trailing limb angle.
I agree. I think that's all very important information. And I think that those are huge things that we as clinicians need to hear and need to reemphasize that, we need to continue to do better for our patients and continue to adapt to what the research and what new technology out there is showing us as being beneficial. Another question I have for you, which kind of leads directly into the biofeedback question is, trailing limb angle is, as you've said, an important concept to be able to direct forces for individuals post-stroke. And I know you're working, as you mentioned, some research opportunities with Tricia Kazar at Emory. What would you recommend to individuals in the clinic as far as different types of biofeedback options, either with or without robotic assistance, to potentially address this issue so that way they can continue to improve their cueing to their patients, different types of biofeedback that they might utilize to help their patients relearn their trailing limb angle?
Yeah, good question. I mean, I think the reason we like trailing limb angle so much is because it's potentially an observable for someone who's in the room with a patient who's in recovery and is practicing. It's easier to see motion than forces, right? So if you're not lucky enough to have an instrumented treadmill, which a lot of clinics have now, if you have an instrumented treadmill, you could show people their propulsive forces directly, like on a screen. That would be the ideal. As we bump down in terms of the complexity of the technology from there, being able to map observable motion to an instruction, I think, is where we want to move. And that's sort of the reason why I think, folks like Mike Lewick and myself and Trish Kizar have got, and also the group in Delaware, led by Darcy Reisman and others, have gotten so excited about, Lua Wad also up in Boston, have gotten so excited about trailing limb angle because it's a motion that is highly correlated to the forces that we know are important, but is observable and maybe even potentially easier to measure with a wearable sensor suite. So I guess that's what I would say. Using motion variables that can be easily observed and coached, and also potentially easily measured in wearable sensors, which are beginning to develop at a very rapid pace for out of the lab use, rather than relying on sort of the underlying forces and powers, which are much harder to measure and monitor.
That makes a lot of sense. I agree. Not everybody has a force plate or a treadmill that can reproduce, forces for them to visualize. So being able to visually look at that and finding ways to cue the patients is a huge thing for clinicians going forward in any size, therapy clinic. One last question I have for you, and we'll discuss a little bit more into kind of what you ended your talk about, kind of the future direction of where you see the research going. You recently released a paper with some of your colleagues at MIT and at Emory as well, looking at bilateral assistance for hemiparetic gait post-stroke with the powered hip exoskeleton. And again, you demonstrated that there was a positive effect on paretic step length and self-selected walking speed. And as you already kind of talked about, combining these two technologies with biofeedback to improve, paretic propulsion, to decrease net metabolic costs for individuals post-stroke. What do you kind of see as the next step or the future for research on this type of exoskeleton technology that's going to kind of bridge these two approaches to improve the gait for individuals post-stroke?
Yeah, that's a great question, and it's exciting to talk about. So, as I mentioned in my last couple slides, I think really making apples to apples comparisons between interventions that are focused on the ankle versus the hip is going to be important. And also personalizing assistance to each individual's particular gait, right? Like we've known for a long time, but ignored because I think everyone was hoping that there might be a one size fits all solution. It doesn't seem like that's true. So customization is going to be incredibly important, and customizing devices in a way that is iterative and productive means using things like machine learning to online tune a device, not just when the person's in the clinic, but also when they're outside using it as assistive technology in the world. So, I would say that algorithm development really is going to be more important than hardware per se over the next decade. We have great solutions already coming from labs like Connor Walsh and others who are developing soft versions of exoskeletons, which I think is going to be important in the future. But yeah, like really figuring out when your particular client / patient comes through the door, what do they exactly need? So how do we make in the clinic assessment and prescription efficient? I think we try a lot of things, but we also rely on these algorithms like human loop optimization to get us a very good initial guess. And then we shop that technology out in the real world and, maybe even rely on data logging and big data analysis to continuously tune that device, even through telemedicine sort of approaches, is going to be where we go. The last thing that I'm really excited about, which I don't think has gotten enough attention recently in the literature or even in industry, is that there seems to be this, are you on the assistive technology or therapeutic technology side? Like if you have a new technology, people will say, is this meant to improve people so that they don't have to wear it anymore? Or is it meant to be a permanent assistive technology for someone who has a condition that can't improve? And I think there's a huge gray area in between those two things that we're not exploring, which is why not start out in the early stages with a device that could be assistive technology later, but right now through its algorithms is behaving as a therapy. And then slowly over time, either you don't need it anymore, which would be great because you can do what you want without the technology, or it's clear that you need some sort of residual assistance and the device just transforms into that in an algorithmic way, right? So the hardware hasn't changed, but the device is able to adapt over time to the individual's needs. So yeah, those are just a few ideas. I could go on for a long time. This is sort of what I love about my job, is being able to think about the next things and trying to do them. But yeah, those are a few, I guess 3 or 4 kind of ideas wrapped up in there that I mentioned.
Yeah, I think that's fantastic. And those are great points. A lot of the things that you hear from clinicians is they're like, what is the carryover? Like if I put this on them, is this something they're going to need long-term, or are we focusing on, neuromotor learning? Are we working on retraining movement, or are they going to have, are they eventually going to get out of this device? And even in the research, when they're talking about longitudinal, long-term studies, what are the carryover for improvements? So I think that that's an incredibly important topic that's going to continue to be discuss down the road of, is it going to be assistive, or are we working on relearning? And I think your take on that is incredibly valuable. And I really think that's a great direction that we need to take the research and really see how we can impact the lives of people post-stroke. I'd like to thank you, Dr. Sawicki, for an incredibly informative discussion and taking the time to speak with us today.
Yeah, thank you so much for having me on. And let me know if in a decade you'd like to hear from us again, because maybe we'll have some exciting things to report at that point. Maybe less than a decade, hopefully 2 or 3 years. But I'll be watching until then. I think I just want to say also that this is really a great forum that you guys have put together. The interaction between industry and academia is incredibly important, and also clinicians. So thank you for doing it.
Thank you very much again, Dr. Sawicki. We loved having you. To our viewers, we hope you find these talks interesting and helpful. Don't forget to like and subscribe to the video using the buttons below. Also, please feel free to use the comment section below to suggest future talks that you'd like to see. We hope you tune in with us again next episode. Take care, everyone.